Hello and good afternoon, friends. Welcome to CEC live transmission. Dear friends, today in this session we would be talking on our series on quantum chemistry. Dear friends, we have conducted 6 sessions and in the previous session we discussed on operators. Today we will try to complete operators and afterwards we will be talking on eigen function. And for this discussion we have once again with us in our studios Dr. Amita Dua. Dr. Amita Dua is Assistant Professor in Department of Chemistry, the Dalhousie College, University of Delhi. Dear friends, if you have any kind of questions pertaining to the lecture, then you can call right in the studio. You can contact us through our toll-free number. Our toll-free number is 1800-110-430. You can ask questions directly from Dr. Amita Dua, but you are requested to call in the last 10 minutes so that the lecture goes uninterrupted and your queries are also resolved. So, taking the lecture forward, let's welcome once again our guest, Dr. Amita Dua. Hello ma'am, welcome to the lecture.
So, hello to all my viewers. In the last lecture, we have discussed about operators, and today we will discuss about the Hermitian as well as linear operators, and I'll also discuss about the eigen function and eigenvalue. So, in the last lecture, I have told you about some of the expression for the main operators which we use in the quantum mechanics. And again you can see the slide. Some of the expressions for the operators are, that is the Laplacian operator. Just see the expressions because we have already done the derivation in the last lecture, lecture number 6. I have discussed all the derivation parts. So just see the expression, that is Laplacian operator, which is del square and equals to del square by del x square plus del square by del y square plus del square upon del z square. The next is the momentum operator. The momentum operator in the x direction is px operator, that is h upon 2 pi I d by dx. Similarly, we have py operator, that is the momentum operator in the y direction, that is h upon 2 pi d by dy. And similarly, we have pz, that is h upon 2 pi I d by dz. And when we add all of them, we get the total momentum operator, which is p operator h upon 2 pi I into the Laplacian operator, that is delta. The next was square of the momentum operator. In this square, we simply take the square of the momentum operator and it becomes minus h cross square del square. And then we have angular momentum operator, that is L operator, and the expressions you can see on this slide we have given for Lx, for Ly as well as for Lz, and these you can derive by using the momentum operator. And the next one was kinetic energy operator, that is T operator. The expression for the T operator was minus h square upon 2m into del square, that is square of the Laplacian operator. And the last one was the Hamiltonian operator. In quantum mechanics, instead of energy, we use the Hamiltonian operator, that you can see that like energy equals to kinetic energy plus potential energy, and instead of E, that is total energy, which we use in classical mechanics, in quantum mechanics instead of E we have Hamiltonian operator, that is H operator, which is given as T operator, that is kinetic energy operator, plus the potential energy operator, that is V operator, which is given by minus h cross square upon 2m del square plus V, that is potential energy. So these are some of the main operators, that is these 6 operators are the operators which we will use in the whole quantum mechanics. During the quantum mechanics, we will be dealing with all these operators. So you have to remember the expressions actually, because when we will solve the numerical problems, then you should know that how to write the expression for these operators. So now today first we will discuss about what is eigen function, eigenvalue and eigenvalue equation. So suppose we have an operator A operator. If suppose the A operator operates on a function, arbitrary function fx, suppose there is a function fx and an operator A operator operates on fx, and on operating this operator on this function fx, if we get a value, if we get a constant value multiplied by the same function, that is the function is again obtained, there are no changes in the wave function, the wave function will remain as such, but it is finally multiplied by constant, then that constant value is known as eigenvalue, and the function on which that operator operates is known as the eigen function. You can see the expression on the slide. I have given the eigen, and this equation is known as eigenvalue equation. So if an operator A operates on a well behaved function, because I have already discussed the well behaved function, and it gives the same function multiplied by a constant, then the function fx is known as eigen function, and the constant which is obtained on solving this, on applying the operator, is known as eigenvalue of the operator, and the equation which is formed is known as eigenvalue equation. You can see, suppose we have this A operator, it is operating on fx, we are getting a constant multiplied, and the function again we are getting the same wave function back. Like you can see an example, suppose we have d by dx and the function is e to the power of ax, and by applying on differentiating e to the power of ax, a is again we get, what is the answer? That is a multiplied by e to the power of ax. So we have the function e to the power of ax, on operating d by dx we are again getting the wave function back. So this wave function is known as eigen function, and the value a is known as eigenvalue. And similarly we have another example, like we have Schrodinger equation, that is h psi e psi. When h operator is applied on the wave function psi, we get the value e multiplied by the same wave function, that is psi, and the Schrodinger equation is also an example of the eigenvalue equation. Now you can see some of the problems on the eigen function and the eigenvalue. I am solving some of the problems so that the topic will be clear to all of you. Suppose there is this question number 1. Just see, show that e to the power of ikx, I is iota, is an eigen function of the momentum operator px. Now everyone should know that what is px operator. Why? Because even in the last lecture and even today also, I have given you some of the expressions for the operator, and the momentum operator was also there. That was the second was momentum operator, and in this question already the px operator is given to you. So px operator is minus I h cross d by dx, and if this px operator is not given in the question, then the student should know that what is the expression for it, because it is not always necessary that the expression is given to you in the exam or whatever. So what is the eigenvalue? So whenever you do a question, always first write the data, what is given to you. Just understand what is your function, that is fx. Fx is e to the power of ikx. They are saying you show that this function, the function which is given to you is an eigen function. So what is the function? That is fx e to the power of ikx, and it is eigen function of which operator? That is px operator. So which is the operator which is given to us? That is px momentum operator is given. So in the answer write what is the function? Fx. What is the operator? That is, instead of a operator we will write minus I h cross d by dx, because you have to check whether it is an eigen function or not. So we have to use the eigenvalue equation. And what is eigenvalue equation? You have to operate the operator on that function. If we get the function back with a constant multiplied, then it would be its eigen function. So now I will apply px operator on the function fx. So what my px operator is? Minus I h cross d by dx. And what is my function? E to the power of ikx. So you simply have to differentiate e to the power of ikx. So the answer would be minus I h cross. See the slide, the answer is solved on the slide. You can see that is minus I h cross into ik. It will come out, because on differentiating e to the power of x, whatever is multiplied by x will come in front of it. So ik into e to the power of ixk. So it will become minus I square h cross k e to the power of I kx, because iota square would be -1, so minus becomes plus, and I will vanish because I have put it the value of I square equals to -1, and it would become h cross k e to the power of I kx. So this e to the power of I kx is an eigenfunction. Why? Because when the operator is applied on this function, we are getting back the function. It is as it is, it will remain same, only a constant value is multiplied. So the eigenvalue is h cross k, and e to the power of, by this we can say that e to the power of I kx is an eigenfunction. Next question, show that the function a to the power of a into e to the power of minus x is an eigenfunction of the operation d square by dx square, and what is the eigenvalue? So in this, my function is a to the power a e to the power of minus x, and my operator is d square by dx square. So in this, we simply have to double differentiate the function. I'll apply the operator on this function, that is a operator is applied on the function fx, that is d square by dx square a to the power of minus x. So when I double differentiate it, I'll get, because a is a constant value, so simply the minus twice negative sign would be there, so minus would become positive. So simply I get the value a e to the power of minus x, and we are getting the function back multiplied by a constant a, and thus my function is same. That is why it is an eigenfunction, and my eigenvalue would be +1. Why? Because the function will remain as such. Now question number 3, you can see question number 3, show that sin 2x is not an eigenfunction of the operator d by dx, but it is an eigenfunction of d square by dx square, and what is the eigenvalue? So I am doing this question in two parts. First I'll operate d by dx, and in the second question I'll operate d square by dx square on sin 2x. So when d by dx is applied on sin 2x, on differentiation, sin gets converted into cos, and the constant 2 will also come out. So answer is 2 cos 2x. Because sin 2x is converting into cos 2x, the function doesn't remain as such, thus it is not an eigenfunction. And similarly, when I double differentiate it, see this next part, that is d square by dx square. First sin will convert into cos, and cos will again convert it into the sin, and thus the function remain the same. That is why sin 2x is an eigenfunction of d square by dx square, and the eigenvalue is -4. Now see question number 4. You have to operate the Laplacian operator. Again, for this one should know what is the expression for the Laplacian operator. On the given function, the function is given to you, that is fx, and they are also asking you to find the eigenvalue. Given that fx is, what is our function given? Sin kx into sin my into sin nz, and what is our Laplacian operator? That is always del square is used. D square by dx square, d square by dy square, and d square by dz square. Now using the eigenvalue equation, that is, we will operate this psi square on the function fx. So my function is sin kx, sin my, and sin nz. So I will double differentiate it on applying on that is d square by dx square. Obviously the x operator, the d square by dx square will only operate on the x function. The y operator will act upon the y function, and z will act upon the z function. So when I apply del square by del x square on the function, then the y and z part will be a constant, and they will come out as such. And on d by double differentiating the x part, that is sin x, it will give you the answer. I've shown in the brackets, that is minus k square. Why minus? Because sin will convert into cos on differentiation, and cos will convert into sine, and that is minus sign. That's why there is a negative sign, and because it is differentiated twice, because it is d square by dx square, so it is k square and sin kx will remain as such. Similarly, when I operate the y part of the Laplacian operator, it will work only on the y part, that is k and z part will come out as such, and y I have shown in the bracket form, that is minus m square into sin my. Again the same thing I have applied, which I have given for sin kx, this is for sin my, and in the next line again for the z part the n will come out, that is minus n square sin nz. In this case x and y are constants. So by this, when we add all of them, then sin my, sin kx, sin my and sin nz, they will come out, and we have three constants with us which I have taken in the bracket, that is minus k square, minus m square, minus n square, and sin kx, my and nz is the function which we have used, that is why I have put it as fx. This function is known as the eigen function because we have obtained the wave function back as such, whereas minus k square, minus m square and minus n square is the eigen value. Now see question number 5. Show that e to the power of ax is an eigen function of the operator d by dx, and also find the corresponding eigen value. So our function is fx e to the power of ax, and a operator is d by dx. Will operate this operator d by dx on the function fx. This will become d by dx e to the power of ax. By this, obviously a will come out. This is the simple differential question. A will come out, and thus because e to the power of ax remains as such, therefore it is an eigen function of d by dx, and the eigen value is a. Again, see the second part of this question number 5. Show that e to the power of ax square is not an eigen function of d by dx. So on differential of e to the power of ax square, we get twice ax into e to the power of ax square. Thus the result obtained is, because the constant which we have obtained is not a constant value, there is a variable in it, that is x, which always varies. That's why it is not a constant value, and thus it is not an eigen value, and e to the power of ax square cannot be an eigen function. See question number 6. Prove that function a e to the power of ikx, where a and k are constants, is an eigen function of the operator p operator and also an eigen value. So you have seen that in all these questions, one should know what are the expressions of the various operators, which is the most important thing which a student should know, and how to do simple differentiation and integral, and nothing else is required. Now see the answer. Suppose we have an operator px. Now what is the expression of px? That is h cross by I d by dx. When x is taken, you have to take d by dx. If it is y, then you will take d by dy. If it is z, d by dz. If it is simple p, then you have to take the Laplacian operator, that is delta, because it includes all the x, y as well as z. And what is the function fx? That is a e to the power of ikx. Now using the eigenvalue equation, because you have to show whether it is an eigen function or not, so obviously we will take the eigenvalue equation, there won't be any kind of confusion for this thing. So using eigenvalue equation, that is we have operator px, it will operate on the function fx, that is h cross upon I d by dx. It will operate on the function a to the power a into e to the power of ikx. So when I differentiate a into e to the power of ikx, then what would be the answer? A will remain as such because it's a constant. So what will come outside? That is I into k, which is a constant, and it will come down on differentiation. So h cross, that I will cancel with the factor I. So we are left with h cross into k into the function, into the the function which is given to you, because again the function is an eigen function of the operator Px. Why? Because on operating the operator we are getting the same wave function back, and the eigen value would be h cross by A. Now you can see question number, there are three more questions. Question number 7, you can see, show that e to the power of ax is an eigen function of the operator del square by del x square plus 2 d by dx plus 3, and what is the eigen value? So we have wave function, that is function e to the power of ax. We have this operator, apply this operator onto this function. So see the expression d square by dx square will apply, because I have already told you the algebra of operators, that is addition. You will apply one by one on the function fx. So my operator is d square by dx square. So first you will apply d square by dx square on the function e to the power of ax, then 2 into d by dx upon e to the power of ax, and then 3, obviously because there is no as such function, so we will simply write e to the power of ax. So when I double differentiate e to the power of ax, then I will get a square out of it. So it will become a square e to the power of ax 2 into a e to the power of ax, because only once differential is done in the second expression, and then 3 into e to the power of ax. So if I take e to the power of ax as common, so I have a square plus 2a plus 3, because e to the power of ax is our main function which is given in the numerical. So instead of e to the power of ax, I am writing fx back, and thus e to the power of ax is an eigen function of the given operator, and eigen value is a square plus 2a plus 3. Next, show that suppose we have a function 3 cos 2x. I have to show that this function 3 cos 2x is an eigen function of the operator minus h cross h minus h square upon 4 pi square d square by dx square. And what is the eigen value? So our operator is minus h square 4 pi square d square by dx square, and our function is 3 cos 2x. So we simply have to apply this operator on the function. So first I will write the operator minus h square 4 pi square d square by dx square. I will write the function 3 cos 2x. I will take 3 out as a constant and apply d square by dx square upon cos 2x. So cos will convert into sine, and sine will convert into cos, because we are doing double differential. Because there is a negative sign and there is one more negative sign which is already present in the numerical, thus minus minus will become plus. I have shown this plus sign over in the second line. So this is plus h square 4 pi square, 3 is already taken as common, and 4 comes because I have differentiating cos 2x twice. So every time 2 will come out. So 2 into 2 will become 4, and then cos 2x. It is simple, a differential formulas which everyone should know, and by this 4 will cancel out with 4 and left with h square 4 pi square 3 cos 2x. So 3 cos 2x is already the main wave function. Thus the constant which is there is h square upon pi square. Thus the function size and eigen function of the given operator, and the eigen value is h square by pi square. Now see, this is one of the very important question of eigenvalue equation, because whenever we talk about the eigenwave function or eigenvalues, we always give Schrodinger equation as one of the example. So this is one of the question which shows that he is asking that Schrodinger equation is an eigenvalue equation, satisfy. See the expression. So what is an eigenvalue equation? Simply this is nothing, this is the equation which will tell you that what is eigenvalue equation, because Schrodinger equation in itself explains everything. So if an operator A, he is telling you that what is an eigenvalue equation. If an operator A operates on a function fx and the same wave function is multiplied by a constant, then the expression is an eigenvalue equation. And the same thing you can see in the Schrodinger equation. In the Schrodinger equation, we have H operator, which is applying on psi, it will give the psi back with a constant E multiplied. So the Hamiltonian operator H operator, when it is operate on a well-behaved function psi, because in quantum mechanics we always say that what kind of wave functions we deal with the well-behaved wave function. So psi is our well-behaved wave function and it gives the same wave function multiplied by the constant E, and such equation is an eigenvalue equation, and thus the Schrodinger equation is our eigenvalue equation. The last question on the eigen function: if psi 1 and psi 2 are eigen wave functions of an atom, suppose there is an atom and two wave functions are there, that is psi 1 as well as psi 2, then prove that any linear combination of these wave functions will also be eigen wave function of the Schrodinger wave equation. Now suppose we have two wave functions psi 1 and psi 2, and the linear combination would be given by what? The linear combination could be given by the expression I have written as total, the psi 1 and psi 2, that is psi, that is C1 into psi 1, because the weightage of psi 1, suppose there are two wave functions, then what is the weightage of first one? That is given by C1, and what is the weightage of the second wave function? That is psi 2. So this will become psi equals to C1 into psi 1 plus C2 into psi 2, and then H operator into psi, because we have to see the eigen wave function, H operator upon psi, and instead of psi just put C1 psi 1 plus C2 psi 2, and then multiply the H operator, because H operator will operate on the wave function. It will come, you can see the slide, see the answer, that is H operator will come in between C1 and psi 1. H operator gives the answer E, and then I have taken E common, that is C1 psi 1 C2 psi 2 and again psi. So it will give you the Schrodinger wave equation, that is H psi E psi. So we'll just take a break, and after the break we'll discuss about the linear and Hermitian operators. Thank So now we will discuss about the linear as well as Hermitian operators. In the quantum mechanics, we always deal with linear Hermitian operators. So one by one I'll take. First we'll discuss what are linear operators, and then I'll discuss about the numericals based on it, and then I'll discuss about the Hermitian operators as well as its numericals and some of the theorems related to the Hermitian operators too. So first I'll discuss what are Hermitian operators, what are the linear operators. By the linear operator we mean that if it is applied on the sum of two functions, suppose there are two functions f and g, you can see on the slide the two wave functions are written, that is f, I have taken two functions, that is f and g. So suppose there is an operator A and we apply on sum of it, then the result is equal to the sum of the operations on the two functions separately. So suppose we have an operator A and it is applied on f plus g, then the answer would be operator A applied on f plus operator A applied on g. So this is the condition for linearity. You can see the example like differential and integral are the linear operators, whereas square, taking the square of something or square root is never ever the linear operators. Like you can see, suppose I take the differentiation of f plus g, then it would be d by dx of first function plus d by dx of second function. Or suppose I take the function c1 f1x plus c2 f2x. Suppose this is a function and I have to integrate. Then how will you integrate it? Simply, you will do the integration part, that is, obviously we will take the constant out of the expression. It would become c1 integration of f1x plus c2 into integration of f2x. So there is no problem. Simply the sum is given and you have to apply on it and the answer comes out to be the same. And thus differential and integral are the linear operators. Whereas when I take the square or the square root of the functions, just see the example. Suppose I have the function c1 f1x plus c2 f2x and I have to take the square of it. At that time we have to apply the formula, that is a plus b square, and that would be a square plus b square plus 2ab, because answer is not simply we are taking, because it is the sum is not a number, it is an expression, like we have c1 f1x plus c2 f2x. So for taking the square of it, there is a formula, that is a square, that is c1 square fx1 square plus c2 square f2x square plus twice into c1 into c2 into f1x into f2x. So both the sides are not same, thus it is not a linear operator. Similarly, if I take the under root of it, if I have a function c1 f1x plus c2 f2x and I have to take the under root, then the answer is not simply the answer, we cannot take the I have to take the under root of the whole number. Suppose I have to take the under root of 2 plus 5. Answer is never ever the under root of 7. It is something different. So that would be c1 f1x under root plus c2 f2x under root. So the answer is not same. Thus the integration is also, thus differentiation and integration, they are linear operators, but taking square and square root, they are not linear operators at all. Now we will discuss some of the problems on linear operators. Suppose we have question number 1, see the slide, it is given on question number 1. Which of the following operators are linear operators? You can understand better from these numericals. Suppose we have an operator A which is x, A operator is x. Operator is said to be linear whenever, what is the definition for an operator to be linear? That whenever an operator is applied on some function, I have taken a function c1 f1x plus c2 f2x, because for the linearity we have to take the addition part, and when x is applied, the answer comes out to be the same. So like I have x as operator, I am taking x and I am applying on c1 f1x plus c2 f2x. So when x is applied, so answer will remain as such, simply x will go and apply on it, and thus x is a linear operator. Like we have d square by dx square. So if you apply d square by dx square, that is the square of the differential d square by dx square, when it is applied on c1 f1x plus c2 f2x, then also there are no changes. You can apply on the two functions separately. It won't disturb the second function. So it will become, I have taken the function as fx, the single differential as f dash x, and the double differential as f double dash x would be our answer. So when I double differentiate f1x, it will become F1 double dash x, which you can see in the answer. This will become C1 into F1 double dash x plus C2 F2 double dash x. Therefore, it is also a linear operator because our addition is not disturbed by this operator. It can simply operate separately on the two functions easily. Now suppose our operator is a cube. We have to take the cube root of some function. Now we have a formula that every student must have read this formula in class 6 or 7. This formula, that is a plus b whole cube is a cube plus b cube plus thrice of ab. So my operator is, that is, I have to take the cube root of some function. So what is my function? I have again taken an arbitrary function, that is c1 f1x plus c2 f2x. I have to take the cube root of it. So my cube root is not simply the cube root of c1 f1x plus cube of c2 f2x. It is something different. Why? Because we have to apply a formula out of it. So my answer would be c1 f1x cube plus c2 f2x ka cube plus thrice ab, that is c1 into f1x into c2 into f2x. So that's why answer doesn't comes out to be what is expected, that is a cube plus b cube. Instead of a cube plus b cube, we have one more factor, that is thrice of a into b, and thus cube root, taking a cube root is not a linear operator. So when we apply cube root on some function, it doesn't behave in a linear manner. Now you can see more examples. Suppose I have an operator, a operator, d by dx square. See the slide, you can see on the slide, we have an operator d by dx square. So I am taking an arbitrary function, that is d by dx, c1 f1x plus c2 f2x is my function. I have to take the square of it because operator alone cannot do anything. You must have some function with you on which the operator operates and show whether it is linear or not, to show whether it is Hermitian or not. You always must have some function on which operator should apply. Because for the linearity, we must have a sum, so that we can show that yes, whenever an operator is applied on this sum, it can be applied separately. So that is why I am taking the function. I am not taking the function as simple psi or simple fx. I am taking the function as if it is some addition, like c1 f1x plus c2 f2x. Now what is the operator? You have to double differentiate it. You have to take the square of it. In fact, what this is telling, it is not double differentiate, it is taking the square out of it. So d by dx will operate on the function one by one. First, my function is c1 f1x and second one is c2 f2x. So first it will apply on c1 f1x, because c1 is a constant, so I have simply taken it as c1, and then d by dx of f1x, and then c2 is a constant, and then d by dx of f2x. On differentiation, the square is also there. You can also see on the bracket the square factor is also the square taken, which we will take later on in the next expression. So first we will multiply it. We will multiply that what is d by dx, on what the d by dx is applying on. So d by dx of f1x is becoming f dash x, and d by dx of f2x has become f2 dash x. Now we have to take that square part. What is the square? What is the formula? A plus b whole square, that is a square plus b square plus 2ab. So what is the expression? What is a and what is b? We have c1 f1 f dash x as a and c2 f2 dash x as b. So by this, that square part is taken. So this becomes c1 f1 dash x square, that is a square, and then c2 f2 dash x square, this is b square, and then twice, that is 2ab, 2 into c1 into f1 dash x, and one more thing, that is f2 dash x is also there. So this becomes 2 A into B, and by this you can see that it is not simply C1 F1 dash square plus C2 F2 dash square, which we want. So the left hand side and right hand side is not same, therefore d by dx whole square is not a linear operator at all. It is not acting on the sum simply because in this the formula is applied, so it is not a linear operator. You can also see one more example of the linear operators. Suppose we have operator A, that is x square minus x, that is 6. Now I apply this x square minus 6 upon C1 F1x plus C2 F2x. First I will apply x square as an operator, and then I will apply 6 as the operator. So x square F1 C1 F1x plus 1 by 1, that is x square C1 C2 F2x, and then minus 6, that is 6 is multiplied with C1 F1x, and then 6 is multiplied with C2 F2x. So by this you can see that simply you can apply x square minus 6 on the two functions separately. None of them is bothering with other one. Thus again x square minus 6 is a linear operator. Now next is the Hermitian operator. This is one thing which I think every student is afraid of, that is what are Hermitian operators. So just concentrate and see the expression for it, because there may be many confusions, but I have done so many numericals to understand. See, what is Hermitian operator? Hermitian operator is nothing. You have to just go by the expression. You can see and just keep in mind this equation number 8, which is most important. You have to check whether an operator is Hermitian or not. To see whether an operator, like we have checked whether an operator is linear or not by applying on some function, similarly we have to check whether an operator is Hermitian or not by applying on some functions. So for this we have to take two functions. So suppose I'll explain you in a very simple manner. So you simply take, suppose we have two functions, psi and phi. Suppose there are two functions and they are eigen function, that is well behaved functions of the operator A, that whenever we apply A operator on any one of them, we get an eigen value. This is he wants to say, okay, suppose we have two eigen functions, that is psi and phi, and there is an operator A operator, and then what is the condition for operator to be Hermitian? So see the expression, that is I am taking the integral minus infinity to plus infinity. See the slide, it's given on the slide, which is very important. Just see the slide, that is minus infinity to plus infinity. You have to take psi star. What is star? Star is the complex conjugate. This you will understand more in the numerical, that how to take and when to take the complex conjugate. That is psi star, A operator should come in the center of the two eigen function. So first I will take the complex conjugate, then take the bracket, and then A operator and then phi. D tau, first thing, this is the left hand side, and then again the integration minus infinity to plus infinity, then write the second function first, that is phi, and then A operator will again come in the center, and then psi, that is star, the total star. So this is the expression. If an operator satisfy this expression, that is when the operator is applied on the said function, and the right hand side, the value of right hand side and left hand side comes out to be the same, then the operator A is said to be Hermitian. Now just see the example. Suppose they said that show that d square by dx square is an Hermitian operator, and obviously to show an operator to be Hermitian, you always must have two wave function, and they have given you two functions, that is e to the power of ix and psi sin x. So you can see, just see the expression. What is all which is required? You need psi star. The one thing which is most important is that you need psi star. There is nothing to do with phi star. One more thing, there is nothing to do with phi star. In both the expressions, that is, see the equation number 8, left hand side as well as right hand side, see carefully that phi star is not required. We need to have psi star with us. So what is psi? There are two functions, that is psi and phi. So psi is e to the power of ix. Then what would be psi star? So it is always complex conjugate, and complex conjugate, you always take the complex conjugate whenever there is iota. Suppose we have a function a plus ib psi, then what would be psi star? That is a minus ib. The psi in front of iota changes, and that will give you the complex conjugate. But suppose we have a function sin x, then it doesn't have its complex conjugate, then psi star will remain sin x. So complex conjugate will come into play. Psi and psi star is different only when there is a role of iota into it. Like in this example, it's given that psi equals to e to the power of ix. Then what would be psi star? Just simply change the sign in front of iota. It will become psi star e to the power of minus x. Now if they ask you that show that the operator d square by dx square is Hermitian, you just keep in mind this equation number 8, solve left hand side and then solve right hand side, and just put them together and see whether they are coming out to be same or not. If they are not coming out to be same, then say that it is not an Hermitian operator, and this is what I'll do. Take d square by dx square. See, just concentrate on the slide. It's solved on the slide in a simplified manner. So I'm taking the left hand side. My left hand side is psi star this is what I want. This is the expression which I want to solve. I'm writing the Hermitian condition, the left hand side of the Hermitian equation, that is psi star a operator phi dx. Why I am taking dx? I can also take dy, I can also take d tau, because I have sin x e to the power of ix with me. I have x function with me, so I have to take dx. So in this case you won't take, because in the expression I have taken d tau, because it is the generalized form. In that case we have x, we have y, we have z, we have both the functions. That is why I have taken d tau. But here we only have the x function, so I have to take dx. So take left hand side, see the left hand side on the slide. This is simply the equation number 8. I am taking the left hand side of equation number 8, that is psi star operator a into phi into dx. Now what was psi star? I have already converted e to the power of ix into e to the power of minus ix. So I will put e to the power of minus ix, and then choose the bracket, put a bracket, and then what is my operator a? D square by dx square. What is my phi? That is sin x. Just simply solve it. What is the double differential of sin x? Sin will first convert into cos, and then cos will convert into minus sin. So there is an introduction of minus sign into it. Don't solve the whole integral. So minus sign will come out, and it will become e to the power of ix into sin x into dx. Now stop. Now again take the right hand side of the Hermitian condition, equation number 8, and that was phi into brackets a operator psi, and then in totality the star of it, and then write dx. Now what is my phi? My phi was, take integration, my phi was sin x. What is my a operator? D square by dx square. What is my phi? E to the power of minus ix. Why I have taken phi? Because my phi was e to the power of ix, because star is there. In totality I have to take d by dx e to the power of ix on the whole star. So d by dx doesn't have any relationship with the star. Why? Because it is complex conjugate, d by dx will remain d by dx. So what is the which is the one which is affected? That is e to the power of ix, which will become e to the power of minus ix. So I have directly written, I am not showing the bracket with the star and then doing the star part, but directly I have written e to the power of minus x into dx. So by this, now I'll double differentiate it. On double differential, because there is a negative sign, when I double differentiate it, minus minus would become plus. And why there is a negative sign? Because iota is also there. On differential, I'll also obtain I square, and I square is minus 1. So again, I'll land up onto the integration of sin x, and then into bracket. The bracket is giving you the double differential part answer, that is minus e to the power of minus ix into dx. So the answer is again minus sin x e to the power of minus ix dx. By this you can see that left hand side as well as right hand side of that equation number 8, and just simply taking that equation number 8 which was the you can see the slide, that equation number 8, that is left hand side and right hand side. I have simply put it the answers, I have simply put it the values of phi A operator, psi as well as psi star, and solved the right hand side as well as left hand side. Because both the sides, the answers are coming out to be same, that is why the A operator, that is d square by dx square, is an Hermitian operator. So this was one of the very simple example just to explain you that what are Hermitian operators. Now there are two very important theorems whenever we read about Hermitian operators. This also comes as question most of the time in your exam. So there are two theorems. First theorem is that eigenvalue of an Hermitian operators are always real. It means that whenever suppose we have an Hermitian operator, and whenever we apply Hermitian operator onto some function, then this function will remain as such with a constant multiplier. It simply means that it follows the eigenvalue equation, and the value obtained, the eigenvalue which is obtained is what? Is real. It is not an imaginary. It may be positive or negative, but if real means it doesn't contain iota into it. Iota makes a thing imaginary. So I'll do the derivation part, that how can you show that. Suppose I have an operator, A operator, and let it be because we have to assume, because we have to show that. So suppose A operator is an Hermitian operator and psi an eigen function, then A would be the real value. This is what we want to show. This is the thing, and we have to prove it. So suppose you can see the slide. I have marked A operator as Hermitian operator, psi as eigen function, and A as a real eigen value. That if it was an Hermitian operator, the answer will definitely comes out to be real. So see the derivation. Suppose A operator is an Hermitian operator and psi is the eigen function and A is the eigen value. So what is the eigen value equation? We have already discussed, that is A operator when applied on psi will give you eigen value, that is A into psi. This I have marked as equation number 1. Now we will take the complex conjugate out of it. Simply take the complex conjugate, take into the left hand side and right hand side and put a star, that is complex conjugate. So this will become A operator psi, that is star, the total thing, and then A psi star, that is A star into psi star. Now multiply, we have two equations, that is equation number 9 and the second one in which I have taken star, mark it as equation number 10. So we have two equations, that is equation number 9 and equation number 10. Now multiply this equation number 9 by psi star and then integrate them. So this equation number 9 will become what? We have taken psi star into A operator psi d tau. I am not taking dx or dy or dz because it is a general thing. The wave function could contain any coordinate. It would be d psi, and then again A psi that is right hand side of equation number 9 is also multiplied by psi star, that is A psi d tau. Now out of it, in this is simply the left hand side will remain as such, and because A is a constant, I am taking A out of the expression. So it will become A integration of psi star into psi into d tau, and this will become our equation number 11. Now first we have multiplied equation number 9 with psi star, and now we will multiply equation number 10 with psi. What was our equation number 10? It was A operator psi star A star psi star multiplied by psi and then integrate. This will become psi A operator psi star d tau and then psi A star psi star d tau. In this also, on the right hand side, take A star as common. It will give you equation number 12. So from 9 I have got 11, from 10 I have got 12, and then left hand side of equation number 11 and 12 are same because A operator, because we are considering that operator A is Hermitian, so obviously the left hand side will remain same. So because left hand side is same, then right hand side would also be same. So by putting the right hand side of equation number 11 and 12 equal by this, the two things gets cancelled and we are left with A equals to A star, and this shows that A is real. So in the next lecture we will do more about Hermitian operators and we'll start discussing about the postulates of quantum mechanics. Thank you.
With this note, thank you ma'am, thank you so very much for giving us a productive session, and friends, if you have any queries or suggestions, then do write to us at info.cec@nic.in. The lecture is uploaded is going to be uploaded on YouTube soon, so keep watching us, keep writing us, and yes, your feedbacks are important. We would be meeting again very soon and would be discussing further. Till then, take care, goodbye. Thank you ma'am, thank you once again.